So today I'm gonna show you how to do Huffman coding tracing. So Huffman coding, we have to follow two steps. First is to build a Huffman tree from input characters, and the second step is to traverse the Huffman tree and assign the codes to character. So why this is called Huffman coding? Let's assume that there is 4 character A, B, C, and D, and their corresponding values. Variable length code is 0, 0, 0, 1, 0, and 1. The coding leads to ambiguity because code assigned to C is the prefix of codes assigned to A and B. If the compressed bit stream is 001, the decompressed output may be CCCD or CCB or ACD or AB. So how to do this? The first step we have to do is we have to I have to put it in the right order, right? So it's gonna be like this. E. Let me write it down here. E2, A3, B5. Oh, sorry, this is D4, B5, and C6. So how do we do this? First thing first, to do the Huffman coding, we have to do it step by step. We're gonna choose the two smallest number and create it and construct it by reheat from it. So 2 and 3 is the smallest, right? So 2 plus 3 is 5. You put it here. And then what's the next step? So let me write again. This one is 4. We're gonna compare 5, 4, 5, and 6, right? So which one is the smallest? 5 and 4, right? But yes, 5 and 4 is the smallest, right? So I'm gonna construct it. 5 plus 4 is 9. So we put it here. Let me delete this. So between 9, 5, and 6, which one is smaller? Definitely 9, 5, and 6, right? So that's why we pick 5 and 6. We create a binary heap from it. 5 plus 6 is 11. And then what do we miss? The only thing we miss is this one, right? We haven't connected it to each other. Every node have to be connected. So 9 plus 11 is 20. And then 20 like this. Remember this. On the left of the subtree is always 0, and on the right is always 1. So I'm gonna write down 0, 0, 0. This 1, this 1, this 0, and this 1. So now I'm gonna construct it. So like this, letter code A 0, 0, 1, B 10, C 11, and D is right here, right? We always start from the root, the topmost, and we go until we see the value, see the node. So 0, 1, D is 0, 1, and E is 0, 0, 0, and this is the final answer. Then the next question. So right now I'm gonna do B3 insertion. So how to do it? What do you know about B3? So for B3 it's a bit different, right? B3 insertion is not like AVL because we have to perform left or right rotation if the node is not balanced. So the first step, I'm gonna do it quick. So what is the step to do this type tree, we're gonna initialize. The first value is the root, which is 4 in this case, and then while the value is not leaf, we do the follow. Find the child of the value, find the child of 4 in this case. That's going to be traversed. Next. Let the child is y. And if y not full, we change the value 4 to point to e. And then if a is full, we split and change x to point to one of the two parts of the value 4. When we split y, we move a key from y to its parents. In the loops, in step 2, stop when x 4 is leaf. X must have space for one extra key as we been splitting on nodes in advance. So simply insert value. For instance, value k to value x. So right now, to make it clear, I'm gonna do some example. So we have to do insertion for this one, right? Let me write down here. So what is the first step? So the first step is we have to choose the first value as the node, right? As the root, right? So 4 is now first step. And then the second step, what we're gonna do, we will insert, we will do like this, right? We're gonna make it to the right of 4, right? Because 5 is less than 4. And the same for 6. So 4, 5, 6 is gone. So what do we have to do next? So the next step is we're gonna check the balance factor. This is the most important. We're gonna stack from the leaf node to the root. This is 0, this -1, which is fine, but however this is -2. So right now I'm gonna have to perform rotation for this one. So 5 is gonna be the middle. We choose 5 as the middle, and 4 is gonna be on the left, and 6 is gonna be on the right. So this is the first important step. So what next? We keep doing that, right? And we have to be careful when we perform rotation. So I'm gonna do it right now. So 7, 5 is less than 7. So 7 is on the right of 6. Now we're gonna check the balance factor. Is 1, which is fine. And we're gonna do that. We're gonna keep doing that. Until we meet our goals. So after 7 is inserted, we're gonna insert 3. So where's 3? 3 is gonna be here. We're gonna check the balance factor. 2 minus 2 is 0. This 0. This 1. This -1 is 0. Okay, that's fine. And now the value 1. So I'm gonna write down here. Value 1 should be on this, right? Yes, it should be this. And we're gonna check balance factor. 2, 3. This 0, this 1, this 2. This is not correct. Okay, so what we're gonna do? We're gonna perform rotation for this one. The same thing. We're gonna choose 3 as the middle value. So 4 is on the right and 1 is on the left. 6 is right at normal. And then after this, we're gonna do 8. Where's 8? 8 is on the right of 5, right? So it should be here. Now we're gonna check the balance factor. What you're gonna see immediately, catch your eye. This one is not balanced, right? Because when we look at 6 is gonna be the important value. The balance factor of 6 is negative 2, which is not appropriate, correct? So we will write the value again. And 7 is gonna be the middle element. 6 here, 8 is here. And then the last step, what we're gonna do? Where's number 2? Where will number 2 end up? You will see it's gonna end up in let me see, 2 is on the left of 5, right? So we're gonna input it in here. 1, 3 is less than. Now the most important thing, we check the balance factor again. 0, 1, 2 minus 1. 2 minus 1 is 1. Fine. This is 0, 1, 2, 3. So 3 on the left. 1, 2, 3. 1, 2, 1. Fine. This is 0, 0. This is 0. This is the balanced binary tree.